Hello, this presentation is part of my study on antenna and today's topic is antenna fundamentals and parameters. In any communication system, the basic idea is to transfer information from one point to another. And to do that, there are two main ways. The first is through transmission lines like wires or coaxial cables. These are guided paths. The second method is electromagnetic radiation, which is wireless, and this is where antennas come in. Antennas act as the bridge between the circuit and free space. As shown in the diagram, the signal starts at a source, goes through a transmission line, reaches the antenna, and from there it radiates into free space. On the other end, a receiving antenna picks up the signal and passes it to the load. So basically, antennas allow us to send energy or information wirelessly using electromagnetic waves. So what's transmission line? A transmission line is simply a path that carries energy from one point to another. But instead of just sending current, it actually guides electromagnetic waves. There are two common types, the two-wire line, which is the most basic structure, and the coaxial cable, which is more shielded and commonly used in high-frequency systems. We typically need transmission lines when the size of the end system is similar to the wavelength of the signal. In that case, we can't treat it like a simple wire anymore. We have to think of it as a distributed system where wave behavior really matters. Now, in circuit theory, we often use two types of models, lumped and distributed. The lumped model works well when the physical size of components is much smaller than the wavelength. For example, if I have a 4 centimeter wire at 30 gigahertz, the wavelength is so large that the wire looks tiny in comparison. So a lumped model is totally fine. But when the size of the structure becomes comparable to the wavelength, we can't ignore the wave behavior anymore. That's when we use the distributed model, like transmission lines. One key point to remember, as frequency increases, the wavelength becomes shorter, which means even a small physical size can act like a long line in terms of electrical behavior. Now, when two points are very far apart, like Earth and the satellite, using a physical cable isn't practical. That's when we rely on electromagnetic radiation to transfer energy wirelessly. Antennas make this possible. They take energy from the source and radiate it into space as electromagnetic waves. But for radiation to happen, one thing is essential. There must be accelerated charges. In other words, the current has to vary with time. A constant DC current won't work, it won't radiate anything. So it has to be AC or a time varying current. That's what creates the changing electric and magnetic fields needed for electromagnetic wave generation. Now, this slide shows how the same wire can behave completely differently depending on the frequency. At a low frequency like 30 Hz, a 4 centimeter wire looks like an open circuit. No current flows, and we can treat it using the lumped model. But at a high frequency like 10 gigahertz, that same 4 centimeter wire does not act like an open circuit anymore. The wave actually propagates through it, so we can't ignore wave effects. In this case, we have to use transmission line theory. So the key takeaway here is it's not just about the physical size. The frequency matters a lot because it changes the wavelength and that changes how the wire behaves. So far we know that time varying current is necessary for radiation. But here's something important, it's not always enough. Just because a current is changing doesn't mean it will automatically radiate energy. For example, a transmission line does carry time varying current, but it doesn't radiate efficiently because the fields from the two conductors cancel each other out. Radiation actually happens when the current distribution is arranged in such a way that the fields don't cancel, like in an antenna. So it's not just about having changing current, but also how that current is arranged. Now, in Communication systems, the second way to transfer energy after transmission lines is electromagnetic radiation. This happens when charges are accelerating, which basically means the current is changing with time. So a steady DC current can't do this. It doesn't create electromagnetic waves. So if we want energy to travel through space, we need time varying current and we need antennas. The antenna is the structure that takes the current and turns it into radiated energy that can travel through the air or space. So now let's talk about antenna system perspective. In a full communication system, the antenna is right in the middle of everything. On the transmitting side, the signal starts from a source, travels through a transmission line, reaches the antenna, then gets radiated into free space. And on the receiving side, signal travels through space, gets captured by a receiving antenna, and then goes through a transmission line to reach the load. So the antenna plays a key role. It acts as a bridge between two worlds, the guided energy inside a circuit and the radiated energy in free space. Now, the antenna's main job is to act as a transition device. It connects the circuit world to free space. Inside a transmission line, the energy is carried as a guided wave, meaning the electric fields are bounded and follow a defined path. When that wave reaches the antenna performs it into radiated wave, which is unbounded and free to move through space. So the antenna basically takes the guided energy and releases it into open space, allowing it to travel over long distances. Now this slide connects Maxwell's equation to how antenna actually work. Like Gauss's law for electric fields written as del dot E equals rho by epsilon naught tells us that electric fields originate from charges. Positive charges make fields spread outward and negative charges pull them inward. So in free space where we assume there are no charges rho equals 0, this simplifies to delta dot E equals 0. Then then we have Faraday's law, which is del cross E equals minus partial B over partial T. This equation explains that a changing magnetic field produces a rotating electric field. That's how electromagnetic waves are sustained in space. So even though radiation starts with moving charges at the antenna, it's actually the interaction between electron and magnetic fields that keeps the wave going, not the charges themselves. Now this is the big picture of how the whole communication system works. It starts at the source where the signal travels through a transmission line as a guided wave. Then it reaches the transmitting antenna, which radiates wave into free space. At the receiving side, the receiving antenna picks up the wave from space, converts it back into a guided wave, and sends it through another transmission line to the load. So overall, it's guided wave to radiated wave to guided wave again. The antenna is the key component that switches between these two modes. When we talk about antenna performance, we usually divide the parameters into two main categories. First, we have the circuit parameters. This describe how the antenna behaves from an electrical point of view. A key example is impedance, which affects how well the antenna connects with the transmission line. Second, we have the radiation parameters. This deal with how the antenna sends energy into space. Important examples include the radiation pattern and gain, which tell us how much and in which direction the antenna radiates. So overall, circuit parameters are about internal matching and radiation parameters are about how the antenna performs in space. Now, mm, now from a circuit point of view, an antenna can be represented by its input impedance ZA equals R plus ZX. Here R is the real part which represents resistance and ZX is the imaginary part which represents reactance. By replacing the actual antenna with its impedance value, it becomes easier to analyze or design circuits, especially when working with matching networks or simulators. This simplification helps treat the antenna like any other circuit component. And here in this slide, in the antenna's input impedance, R is the real part of ZA, and it represents energy loss from a circuit perspective. These are two sources for this loss. RD stands for conduction or the electric loss. This is the unwanted part. It turns energy into heat. And RS is the radiation resistance. This is actually a good thing. It means the antenna is successfully radiating energy. So the total resistance is the sum of both R equals RS plus RD. Ideally, RD should be small and RS should dominate. Here, radiation efficiency represented by the symbol eta tells how much of the input power is actually radiated by the antenna. And the formula is eta equals RS by RS plus RE. This means the more power going into radiation RS and the less going into loss RE, the higher the efficiency. And efficiency can be written in different ways as a decimal, as a percentage, or in decibels. Higher and higher it means a more efficient antenna that wastes less energy. Now VNA is vector network analyzer. It is used to measure how radio frequency or microwave signals behave in a system. It's key tool and antenna testing. The VNA gives the total input impedance of the antenna written as ZA, but it can't tell how much of that is from radiation resistance RS and how much is from loss RE. It just shows the combined result. So even though the radiation efficient formula is simple, eta equals RS by RS plus RE, it's difficult to measure RS and RE separately in practice. That's one of the limitations of using only a VNA. Now, this imaginary part of the antenna's input impedance is written as X, and it represents the stored energy near the antenna, not the radiated part. If Zx is positive, it means inductive storage, and if Zx is negative, it means capacitive storage. But an antenna's main job is to radiate, not to store energy. So the for the best radiation performance, the stored part should be minimized. That happens at resonance when x equals 0, meaning the reactive part cancels out and the antenna is pure resistive, ideal for efficient radiation. So to wrap things up, transmission lines are used to guide energy while antennas are what actually radiate into space. For electromagnetic radiation to happen, there must be time varying currents. Steady DC doesn't work. Antenna performance is described using both circuit side parameters like impedance and radiation side parameters like pattern and gain. And behind all of this, Maxwell's equations are the foundation. They explain how electric and magnetic fields interact to create radiation. These are the key ideas that define how antennas function in real system. That's the end of this presentation. Thank you for listening.